that is, we'll take off from that point. So last time I think we were talking about Markov random fields, and we were talking about non-Gaussian Markov random fields, and I started to talk about the concept of the influence function and the potential function, and how you develop a framework for incorporating those into non-Gaussian prior models, Markov random fields. And the reason you do that is because they can capture edge structure and higher order detail. Non-Gaussian behavior is actually in images, okay? So I guess with this point, one other thing is that I think what we're going to do is move back the exam to the 18th, okay? I guess it's October 18th. Because it's kind of coming up fast, and there's a number of people who are going to be really busy that week, so I guess that's the week of October break. So, in an effort to not exercise cruel and inhuman punishment, I'm going to move it back to the 18th, okay? But it will be a 1-hour exam, so for the off-campus people, you're going to have to set up a proctor time to get that to get that exam done. I want it to be a 1-hour exam, so basically it doesn't take an infinite amount of everybody's time. But the exam will be based on on homework problems, okay? I'm basically going to just list homework problems from that you can assign, and that'll be the exam. So what is the best way to practice for the exam?
Do the homework.
Do the homework. It's an amazing thought, okay? So, the exam is going to be composed of what? Homework problems, okay? And the best way to know how to do the homework problems is to do the homework, okay? Okay? It's a very simple formula, okay? So, and you have until the 18th, and this is the 27th, right? So you basically have 2 weeks. Yeah. So that'd be a Friday.
Yep.
2 weeks from today. 3 weeks from today. You have 3 weeks. 3. Ein, zwei, drei. Or whatever. Okay, good. So I'm going to go over to the document camera. Okay. Now, pen. Here we go. So last time we talked about, we talked about, last time I think I did some extra stuff. So I talked about influence functions, didn't I? No, I talked about some other things, I think. What did I talk about last time? I'm forgetting. I got off on a little bit of a tangent. We had some extra time and there were a number of questions. What was the question? Excuse me? Yeah.
Convex function.
Oh, I talked about convexity, because we're going to need that, right? So I figured I may as well cover it anyway. But I talked about convexity, okay? Now, what will happen is that, so these are the distributions that we're going to consider. This thing here is the distribution of this is what's called a Gibbs distribution, okay? It's a Gibbs distribution because it's an exponential of a sum of functions, where the functions are functions of groups of pixels that are cliques. In this case, they're pairs, okay? A clique is a set of points which are all neighbors of each other, okay? So the concept of a clique, so in high school, okay, everybody's been in high school. They have things called cliques, okay? A clique is a group of people, okay? And every person in that group is friends with every other person, okay? So a clique is a set of points in a graph where every person every node in that graph is a neighbor of every other node in that graph, okay? It's a fully connected subgraph, okay? So that's called a clique. So for now, we're just going to consider pairwise cliques, okay? So it's going to be like, we'll just consider pairwise cliques, okay? And so therefore, this will be a Gibbs distribution. Now, when something is a Gibbs distribution, it's also a Markov random field. Because if I calculate the conditional distribution of one point given all the other points, I can go through the calculation, and that's what this is here. this calculation shows that, if I go through the calculation, it shows that, in fact, the conditional distribution of a point given every other point in this case will just be a function of the neighbors. And the neighbors, okay, are defined by basically the set of all pixels which are members of a clique that contains the pixel F. That was a long sentence, okay? But basically it's like this. So you have a pixel here, right? Okay. And then, okay, this guy's a neighbor, okay, so that's a clique, okay? So this guy's a neighbor, so that's a clique, or that's a clique, so that's a neighbor. So this guy's a clique, in a clique with this, so that's a neighbor. So basically, any point which is in a clique with the pixel in question is a neighbor. Okay? So one way of thinking about it is that, so you take the most popular person in high school, okay? So the most popular person in high school, this would be like the captain of the cheerleaders, okay? If you went to school in the United States, this would be the captain of the cheerleaders, okay? So the captain of the cheerleaders belongs to a number of cliques, okay? So they belong to that clique, okay? And they belong to this clique, okay? And they belong to some other clique, this clique, okay? Okay? So there's 3 different cliques, right? And then the neighbors of this point are all the points contained in the union of all the cliques that contain the captain of the cheerleaders, okay? So these are the neighbors, right? By the way, neighborhood relationship is symmetric then, because it's easy enough to show that since a clique is a set of points which are all neighbors of each other, that this point must share the captain of the cheerleaders as a neighbor also. Okay? So, so that's a little more general. We're actually going to cover this more general definition, but right now we're using a little more restrictive definition, okay? So that's this. And so, okay, so what does this mean? It means this. It means that if you're a Gibbs distribution, then you're a Markov random field. Okay? You can actually show, and we'll talk about this later, that the other direction is also true. If you're a Markov random field, then you have to have a Gibbs distribution. Yeah?
So I had a confusion, like in that summation, are we counting the difference twice?
This is a very good point, because I know a few people wasted a lot of time in their programs because of this issue. You got to keep track of whether you're summing over cliques or whether you're summing over neighbors. Okay. So if you know, in some of the formulas we have the sum over S and R, a member of T, of some function we'll call BSR, rho of XS minus XR, right? So this is a sum over cliques. And you have to be careful, because what people will often do, because they're kind of used to doing this from implementing FIR filters or whatever, right, is that they'll take this pixel, right, and then they'll calculate whatever the function is for its neighbors. Its 4 neighbors, say, right? And then they'll go to the next pixel and they'll calculate the function for its 4 neighbors, right? But the problem is you've counted that pair of pixels twice, because you hit it twice. You hit it when you have S and R, right? So you calculated it when you took S comma R, and you also calculated it when you took R comma S, right? So you have to be careful about that. And that's why, in fact, I actually did mention this last time, but it's, you have to actually do it wrong a couple times first before you actually notice that it's important. Is that here I'm summing over for each S. Oh no, hold on. Here for each S I'm summing over all the R's. So every pair of pixels gets counted twice in that case. But when over here, I'm summing over pairs. So every pair of pixels is only counted once. Right? So that's why there's a factor of 2. That 1/2 there accounts for the fact that every pixel is counted twice. You know, the way of thinking, another way of thinking about it is that, there's a lot of ways of thinking about it, is that, you know, you have, this is, you know, the pixel index this way, and this is the pixel index this way, and this is a function, right? It's a symmetric function. So this is a symmetric matrix. So if you sum all the elements of the matrix, you'll you know, if you have to sum all the elements of the matrix, you could just sum the diagonal and then the upper element, and just take the upper element and multiply by 2, rather than summing over all the elements, right? So it's symmetric. Yeah?
Now, that works only when there is a circular boundary condition, right?
Yes. Well, no. Well, it depends on what your question means. It depends on what the word "it" means in your question.
Okay, sorry.
Or that, okay? There are a few pronouns floating around there that are not precisely defined enough. So what happens is that, let's say this is your image, okay? So you come to this point here, okay? So if you calculate all its neighbors, then you'll calculate that neighbor of it, right? But then when you come over here, you'll calculate this neighbor of it. So you'll count that relationship twice.
Right.
Okay? So in fact, even if you, no matter how you handle a boundary, you'll hit every pixel pair twice. Okay? So you have to be careful about that, is what it really comes down to. You know, that's why it's better, I know, it's better really thinking about it as, I'm missing a page here, shoot. It's better, in my opinion, to think about it in terms of this sum over pairs, okay? And then think about it, you really need to go through this little equation here at the bottom of page 100, because what it's saying is that you can calculate the conditional distribution of a pixel given its neighbors, given all the other pixels. Okay, it's only a function of its neighbors, but its neighbors are defined as any pixel which it belongs to a click in, okay? So that means that the neighbors of a pixel on the boundary are different, because there is no pixel out here, so it's not enough to click with it, okay? So that just gets dropped. See, if you think of it this way, for this last lab, a lot of people have problems with it, okay? Because they think about it as a filtering operation, but it's probably not the best way to think about it. In the middle of the image, it is, okay? But, okay, there's two bad ways of thinking about how to do this. One is as a filtering operation, and the other is as a matrix. I mean, if you literally try to populate the matrix, I mean, you can do it, but it's crazy, because the matrix is huge. So the way you want to think about it is in terms of, at every point, what the correct operation is based upon what the assumed clicks are in your sum, okay? I don't know if that completely makes sense. It's one of those things you just have to do to really understand, because I can write the notation down, but I'm not sure it conveys the intuition. Are there any questions about this? I know it's an important point. It's maybe the most important thing. If you don't understand this, everything else is not very important.
It's actually a more basic question. In the distribution, there's a normalizing factor, right? And sometimes it's called partition function, I think.
A partition function, yes.
Why is it called like that?
Oh, well, I don't know what the actual history of why it was named that, but it comes out of thermodynamics, and the partition function is Z is equal to, the sum over all states of the exponential minus u of x, where this is the energy. And it's a normalized constant. It turns out that the partition function is very important in thermodynamics. How many people have taken thermodynamics? Did you talk about the partition function?
Yeah.
Oh, okay. If you take statistical thermodynamics, you'll definitely talk about the provisions. If you take conventional thermodynamics, like kind of engineering thermodynamics, I don't know if they talk about it a whole lot, but I think they forget. Maybe they don't. I don't know. You're a mechanical engineer, right?
Yeah.
So you should know a lot of thermodynamics, right? You take a lot of thermodynamics. Do they talk about the partition function a lot? They
Not in
differentiate it with respect to different things like temperature.
Not in engineering somewhere not that much.
Excuse me.
Not in engineering somewhere like the normal. In
Okay,
statistical,
It's more discussed when you talk about the derivation of thermodynamics from basic principles, which is statistical thermodynamics. I actually have a little section later on where I do like a really quick derivation of it all, okay? And it's like just a few pages, it's in the appendix. You might want to take a look at it. And it just quickly derives the fact that the Gibbs distribution or the Boltzmann distribution is the distribution you get when you assume that the expected energy is constant and you maximize entropy. And then from that you can actually derive a few other things. If you put a variable here, beta, you can differentiate this with respect to beta, and then what happens is then z becomes a function of beta. We'll see later that beta is equal to 1 over T, where T is temperature. So this is the physical. This is how temperature is actually defined in real physical systems. Okay, any other questions? So now,
Professor, I have
yeah.
very quickly. Why do we just consider pairs of clicks and not the entire set of clicks?
I'm sorry, say that again?
Why do we consider just pairs of clicks?
Because it's simpler right now. Later we'll consider more.
Okay, because I was wondering for an 8-point neighborhood system, all 2 cross 2 pixels are 8-point clicks. No, that's the highest number of clicks. We can have up to 4-point clicks, right?
Yes, that's a very good point. So if you only have nearest neighbors, like a 4-point neighborhood, then the biggest click you can have is 2 points, right?
Right.
But if you have an 8-point neighborhood, then if you have 4 points, this is a neighbor of this, this is a neighbor of this, this is a neighbor of this, and this is a neighbor of this, so you're good. So this is a click.
Right.
Okay, but we won't talk about that for a little while. Only because this is simpler, and it's plenty of rope to hang ourselves with. So, all right, okay. Now, I think I mentioned last time you can have these various functions, but they're not convex. So now, the problem with convexity is important for a couple reasons. It allows you to solve optimization problems efficiently, and be sure that you got the global minimum. But it also ensures that you don't have, I think I did this last time, you don't have a situation like this, where you can suddenly jump from a minimum here to a minimum there, okay? So if that happens, then the result can be discontinuous. And that's not just a theoretical concept. You can actually easily create a situation like that. So here's an example where I did this like a zillion years ago, that you have a signal, the signal is just ever so slightly different, okay? But when you solve the optimization problem, the one goes here and the other one goes there. So you sort of jump between 2 different minima is essentially what happens. And so that can create unstable behavior. In an image, what would end up happening is that if you had that kind of behavior, you might find that you had, let's say you had like a circle like a light circle in a dark region, right? And it was very noisy, okay? Then as the circle got lighter and lighter and lighter, then what would happen is eventually it might just get blurred in, and then just slightly darker, and all of a sudden you get a sharp edge. So effectively what happened when you go to recover that, you might get something like this, right? It'll blur in some spots where the noise is just a little bit too low, and then you'll get sharp edges somewhere else. So that, depending on your application, that might be a good thing or it might be a bad thing, but in a lot of applications, that would be kind of visually I mean, you don't want the algorithm making those kinds of decisions for you. You kind of just want to look at the image. And so in a lot of applications where a human has to interpret the data, you don't necessarily want that kind of behavior. It's not desirable. So it's best avoided, okay? It's not necessarily bad, but it can be bad. So that actually leads you to use various cost functions that are convex. So there's a lot of convex functions that have been proposed, okay? And but generally speaking, the convex functions tend to have, and you should read this stuff carefully. And recently, by the way, there's been a huge interest in reinventing all these concepts, okay? So you can go back and read a paper and rewrite it, okay? So then what you do is, so one thing is that, okay, so one, and I like to think of it this way. So you have a quadratic function, right? Okay, and the derivative of the quadratic function is linear like this, right? So then what happens is, one possibility is you can say, well, I'll make it quadratic near 0 because that's the simplest function which has two derivatives, right? If it's like a Taylor series approximation to a function. So if you know the function has to have derivative 0, 0, it's got to be symmetric, and you don't want the derivative, so the first derivative of 0 has to be 0, right? The second derivative needs to be greater than or equal to 0, because if it's equal to 0, if it's less than 0, then it would actually go down. We can't have that. So it could be 0, but it has to, or it could be greater than 0, okay? And if it's less than infinity, the second derivative could be infinite, okay? But if the second derivative is finite, then locally you can model this as being, with the Taylor series, as being quadratic. So this is sort of like the first order representation. Okay? The only other possibility is the second derivative is 0 or infinity. Okay? So if it's quadratic near 0, and then you make it say, okay, well now, you want the function to be convex. For the function to be convex, the second derivative has to be monotone increasing. Because I'm sorry, the derivative has to be monotone increasing, which is to say the second derivative has to be positive. So that means the influence function can't go down. So the thing that's the least convex of all functions that's convex is, whatever that means, is a function that just plateaus. Because if it comes down again, it's non-convex. And if it goes up any faster, well, it's more convex. Okay? So this is the sort of the least convex function, which is also quadratic in the center. So it's going to be like this. And that's the Huber function. So Huber suggested it originally for other applications. Okay? And this is a nice function because it's convex and it's continuously differentiable, and its derivative it has two continuous derivatives. Okay? So well, actually not, because that isn't differentiable there, but that's not very important. It's differentiable at 0, that's the important thing. Okay? So that's fine, and then now the problem is you typically have to pick this threshold t. And the idea is that anything above t is an edge, and anything below t is sort of region that's smooth. Okay? So, but at least you don't have non-convex behavior. So you don't have this really it's first of all convergence when you do optimization is well behaved, and you'll get the global minimum. And second of all, you don't have this unstable kind of behavior when you use it as a prior. Okay. Now another function that you can use is you can use something like delta to the p. Okay. Now if delta to the p. So let's say it might be say delta. I'm just drawing this. I don't know, the 1.1, right? And then if you differentiate that, the derivative of delta to the p is going to be delta to the p minus 1 times P times the sine of delta. Okay? So it's going to look like, so if this is 1 plus 1, then that would be like delta to the 0.1 times the sine of delta, right? And then the other thing's a constant, so I won't worry about it too much. So it's going to kind of look like this. So for instance, if this was, that's correct, yeah, that's correct, right?
Over P. Delta T over P.
Let me look at this just to make sure I'm not doing something dumb here. Yes, that's correct. Right. So now, if T is, say, 1.5, then this would be 0.5. Right, so this would be like a square root. If this is to the 1, then it's a straight line. So as this becomes smaller and smaller, it kind of becomes more severe. Right? And this is a convex function, but the problem with this function is that the derivative here is infinite. Okay? So the second derivative, the second derivative of 0 is infinite. Okay, so that's kind of not good for various reasons that we'll discuss later. That causes some problems, but it can be dealt with. It's a technical difficulty. Okay, but and then if you make delta just if you have P equals, well, first if P equals 2, you have the quadratic case. So that's the Gaussian. But if P equals 1, then you have the case of the absolute value, right? And in that case, then you have a dump like this, and this is called total variation. Also, for some odd reason, they call it compressed sensing sometimes. Well, they call it use. When they use it, sometimes they refer to it as compressed sensing. I don't really understand the logic of any of that. That's fine. Okay, now the key issue though is this: when you're doing quadratic optimization, when you do optimization, when you do, so let's say you have a two-dimensional space. So this is x1 and this is x2, right? And you have, so x equals x1, x2, right? So you say, okay, well, I'm going to take the norm. The norm is of x, right? And you say, well, I'm going to take the p norm, right? So the p norm is the sum from I equals 1 to, say, n, of xi, absolute value to the p, and then you take the p as root, okay? I forget what the notation is for this. Should I just put p there? Yeah, all right, let me write it down less ambiguously. I equals 1 to n of the absolute value of I to the p, and then this is the 1 over p, right? Okay, now, if p is equal to 2, right, then this is the Euclidean norm, so that's a circle. Right? If p is equal to 1, you get a diamond like that. So what happens is, and now if p is anywhere in between, you get some kind of shape that falls somewhere in between. But the point is this: when p equals 1, okay. Oh, what am I drawing? You probably don't know what I'm drawing. Okay, I'm drawing the curve associated with the norm of x, the p norm of x is less than or equal to 1. Okay? So those are essentially contour plots associated with equivalues of p. And actually, if p is less than 1, you even get a more extreme behavior like this. So that's p equal to, say, 1/2. I'm just making something up, okay? So, if p is less than or equal to 1, then this will just be non-differential, have corners, sharp corners, okay? And an important thing, now often people will call this, they'll call this the p norm. Now, it used to be that people were pretty careful about this, and a norm had to obey the triangle inequality, right? So, for something to be a norm, it has to have certain properties. It has to be semi-linear. I mean, some people here must be taking real analysis because they're really engaged on this way. They have to be semi-linear, and they have to have a property that, so it has to have a property that alpha times x equals alpha times the norm of x, okay? So I'm messing this all up, okay? And it has to be this, that the, if this thing here equals 0, then x is, as in, the vector of length 0, right? But it also has to have the property that it obeys the triangle inequality, okay? It turns out that obeying the triangle inequality is equivalent to the contour step being convex. So when p is less than 1, it's not a norm. But people say that. They call it a norm. They call it the p norm, okay? Even though it's really not. And in particular, what's really become popular in recent years is what they call the zero norm, okay? Which is the p0 norm, which is the limit as p goes to 0 of the p norm, okay? And the p0 norm is, of course, not a norm because it's not convex, because it's a series of things that are not convex. Well, that's not a proof. I mean, it could be, but it isn't, okay? And all it does is it counts the number of non-zero elements in the set, okay? Yeah, I'm going to have to prove that, because it bothers me a little bit. But, okay, anyway, the point is this. If you're doing an optimization problem, right? So you have, say, p equals 1. And you want to find, you want to solve a problem, say, y minus ax norm squared. You want to minimize this, right, subject to the constraint that the p norm, that the 1 norm, is less than or equal to 1, right? Or something like that, right? Then, actually, that's a stupid. Oh, no, that's the problem. Okay. Then what will happen is that, the contour plot, the contour plot associated with the constant value of this argument here, y minus ax, will be quadratic, because this is a quadratic expression. So therefore, it'll look like this. So quadratics look like footballs. So you have a point here, and then there'll be a football. We went over this, right? You guys know that this is a football, right? Okay, and now, of course, I drew the football in the wrong place. So by the time it gets out here, okay, I didn't draw that very well. What will happen is there's a pretty good chance that the football is going to touch the corner first. Why? Because if you drop a cube on the floor, you know the corner's going to hit first, right? So let me try that. Here's a cube, otherwise known as a 9-volt battery. Okay. If I drop it, you see, the corner hit first. Right? Okay, why? Because it sticks out. Okay? So the corner is going to hit first. Okay? Now, if the corner hits first, what does that mean?
Zero in one dimension.
Huh?
0 in one dimension.
One of the dimensions is zeroed out. Right? This dimension here, so this is x1 and this is x2, it means that x1 equals 0 as the solution. So what's going to happen is that when you have these kinds of constraints on a problem, and you say the L1 norm has to be less than or something, the solution is going to be sparse. It's going to be sparse. And it's even going to be sparser if you make p less than 1, but that's not convex. So this is a convex function, but it will generate a sparse solution. If the p is greater than 1, is the solution going to be sparse? No, because then the corner is going to be round. Actually, that's exactly what really happened, because I actually lied to you a little bit, because if you look at the corner of the battery, it's actually just a little bit round, okay? Okay, so it's not exactly on the corner that it's going to hit. There's a little bit of a roundness there, but yeah. So the solution is going to be sparse, okay? But now what happens is this. You go, oh, well, if you do the minimum, you have a constrained minimization problem. x1 is less than 1. And you want to minimize that subject that you're subject to this constraint. You want to minimize the norm of y minus ax squared. Now, everybody knows if you have a constraint optimization problem, the first thing to do is to turn it into an unconstrained optimization problem, right? And how do you do that?
Some constants of difference.
Excuse me?
Some constants or some difference of that thing?
Yeah, you're very close. There's a particular methodology, it has a name. You use the Lagrange multiplier, right? So the constraint here is that the solution is actually going to fall on the boundary this thing equals 1, so I may as well just make it equal, okay? So, because you always meet the constraint, right? So, instead what you're going to do is you're going to convert that to the minimum over x of the norm of y minus ax squared plus lambda times the norm of x1, right? Well, that's just like the kind of problems we've been looking at. This part's the same as it was before, except for this part now is an L1 norm of x. Now, here, you know, when you solve this problem, the solution will be sparse. And the sparsity of the solution will increase as lambda increases. Because as lambda increases, you're making the solution, you're making x smaller, is essentially what happens. But the sparsity will increase as lambda increases, okay? So, there's a lot of interest in using L1 norms because they create sparsity. Alright? L1 norms create sparsity, but the problem with L1 norms is, well, sometimes L1 norms are great, and there's a lot of work going on. Actually, so I talk about this on here, and then sometimes when you do total variation, actually what you want to do is take not there's differences between adjacent pixels. So you want to take the absolute value of the gradient. So that gives you an isotropic function. So this is a sort of variation of the theme that I won't cover in detail. That can be advantageous depending upon how you're implementing it. But when you're doing the optimization, now what happens is that the cost function minimum has this, non-differentiable edge in it, and the minimum will often fall along the edge. So when you do this optimization, it's not differentiable there, so you can't use gradient descent. And coordinate descent won't work either, because what happens is this. I think you have a homework problem on this, but let's say you have the function x1 is the x-axis and x2 is the y-axis. So you have x1 minus x2, absolute value, right? So that's your cost function you want to minimize, right? And then say plus x1 plus x2 squared, right, times a really small number, okay, that's positive. So that's your function. Well, what will happen is that the minimum will basically, well, first of all, the minimum will be at 0, okay? But it'll it'll fall mostly along a line like this, but it'll increase ever so slightly because epsilon is very small, right? So maybe this is very small. Okay, and but you'll stay kind of close to here. Okay, so now what will happen is if you do coordinate descent, if you start here, so let's say you start here and you do coordinate descent and you minimize on x first. Well, the first thing you'll do is you'll go right to here. Okay. Then what will happen is you try to minimize x too, but now when you move in the opposite direction, you're stuck in the edge. Okay. It's as if you got like a little piece of dirt in a crevice and you can't get it out, right? So you got a perfect edge there. Like the piece of paper is folded very tightly along an edge, right? Like this. Maybe I should take a blank piece of paper so as not to confuse matters. So you take the piece of paper and you fold it along the edge. And you're doing minimization. You can kind of see this in 3D, and you get stuck in that edge, right? So the only way you can move along that edge is if you move along the direction of the edge. If you try to move obliquely to the direction of the edge, you'll just get stuck in the crevice, right? It's like a little kid riding a tricycle, and they hit this bump, and their wheel gets stuck in it. So the only way you can move is if you move along the edge, okay? So the problem is, and gradient descent, you can't do anything because you can't even do the optimization because you can't compute the derivative. It's not differentiable at that point. So there's a lot of problems, and I won't talk about any of it. There are a number of methods that have actually come out, really become popular in the last few years, okay? They've sort of been around, but I'm not sure they were widely known, that allow you to solve these kinds of problems. One of the most there's a few methods, but probably the most robust method I'm familiar with is this thing called augmented Lagrangian, and it's actually called ABNM. Okay, and the technique you can use to handle a case like this is doing L1 norm minimization. But I won't go into it. The other thing you can do to get around L1 norm minimization is that you can take this Huber function, so you have the L1 norm, and you just put a little tiny piece of little quadratic here just to smooth it out a little bit, okay? And then, so you make t here, so you make t small. And that way it's not non-differentiable at the bottom there, and you don't get perfectly stuck, okay? So I just want to make you aware of the fact that L1 norm is popular because it causes, so the takeaway message is that L1 norm is important because it creates sparsity in your solution. And we'll later see sparsity is important because it reduces the number of variables you have to estimate. And it's also but that minimizing with the L1 norm is sometimes requires specialized techniques. Okay, now, so with that said, in the lab, we're going to mostly focus on the LP norm because it's easier to deal with, and it gives you substantially the same results. And for imaging applications, the problem with the L1 norm is, you get the image quality. Okay, so the L1 norm, you can adapt particular methods. So, okay, right now, everybody's going crazy with the L1 norm, and I've heard numerous people say, if there's like, it's always better, or the LP is always better when P is less than 1. I mean, these are really ridiculous statements, because it depends on the problem you're working on. For some applications, it might be very good, and for other applications, it could be very bad, okay? But one thing is that when you use L1 value, you tend to get solutions which are piecewise constant, because it's the so-called total variation, okay? Because essentially what will happen is it tends to create, it wants to make the derivative sparse. So here, if you look at the derivative of a function that's a step function, its derivative only, it changes in a few places, so you get a very sparse derivative, and the L1 norm likes that, okay? But for real images, that can create an image which has a plasticky look to it that people don't like. So in radiology, for reconstruction of CT images, this would be like highly undesirable, okay? So you can get some miraculous, wonderful results that look really fantastic if you squint and stand back 30 feet, okay? But if you look really close at the image, it's got unacceptable artifacts in it, okay? So you need to usually soften that. So one way of doing it is with the Huber function, where you put a little ball at the bottom of quadratic. Another way is to use a P norm, okay, which is what you'll do in the lab, because that's easy to implement. And then another possibility is that there's this thing that's a little more complicated that I personally like. It works nicely for a lot of applications. It's something we actually did, which is that you create this function which looks a little messy, but essentially what happens is this function is quadratic. You can have it looks like x to the p for small values of x, and it looks like x to the q for large values. So, for instance, q, and where q here is less than p, less than or equal to p. So typically you might take p to the 2. And you could take, say, q equals, say, 1.2 or something like that. But it's sort of or 1.1 or whatever you want. Or if you made it 1, it would be like a Huber function, right, in that case. So it allows you to control the section near 0 and the section far from 0 separately. Usually that corresponds to regions within a smooth regions and regions across edges. So this would model the edge region, and this would model if it was like a computer construction, this would be soft tissue or smooth regions in the image, okay? So, you're going to actually implement this in the next lab, right? I think you're doing that soon. And there's not a whole lot of time. One issue is the scaling parameter. You should read this. Maybe I won't go into this in detail. It's kind of an advanced topic. It's not absolutely critical to understand, but there is this issue of scaling. So if you put the sigma inside of this function, essentially what happens is that you're saying that if I change sigma, I change the amplitude of x. You assume the amplitude of x. Inevitably, you have to adjust for this in real life. So read this section. But the other thing we really need to talk about, and I haven't gotten to yet, is the next section is the line search stuff. So I just more or less finished this chapter of section. Yeah, I know. I'm out of time. So we more or less finished this section on the non-Gaussian prior. Read it carefully and do the problem. And then the next section we'll talk about, now the techniques for optimization within non-Gaussian priors are quite a bit different. There's a lot of tricky issues there. So, and then you're going to implement that actually in the lab, And the last is sort of a toy example. You'll get the basic idea of how to write a program. Bye. Thank you.